Physics in 24 Problems. Here we go. Chapter 27 from Halliday Resnick and Walker, 9th edition. So I'm solving 24 problems out of the book, kind of like give you an overview of the whole course. You can find the playlist down below. Let's get to it. I'm going to explain the problem, and then I will talk about the physics, and then I'm going to solve the problem. So here's the problem. It's number 39 from chapter 27. There's two batteries, and they have internal resistance, but they're identical batteries. So they have an EMF of E, I think they give it as 12 volts, and then an internal resistance of 3 ohms. And they're hooked up in parallel. And the parallel combination of batteries is connected to a resistor R. And so the question is, what value of R will produce the largest power dissipated through that resistor? So we want to find the value of R for the greatest power. So that's a pretty good problem. I like it. Got a lot of different aspects to it. So there's a lot of different kind of problems on circuits in here, but I think this one's just fun. Okay, let's just get to it. So we already talked about Ohm's law, we talked about capacitors, we talked about a bunch of stuff. So, but in this chapter, really, it's all about circuits. So let's just start with our basic circuit. I'm going to draw a circuit like this. I know it's silly. And I picked this up from Matter and Interactions, a really great textbook. So here's a battery connected to a wire, and the wire has a smaller part of the wire. So this is like the hookup wires, and that's my resistor. And this battery is like a capacitor. So let's just imagine for now it is a capacitor. So if there's a capacitor right there, we know we have an electric field going that way. And then this, since this is connected to a wire, you actually get an electric field in here too. Actually, this is going to be much smaller, and it's going to be in the direction of the wire. And then in here, it's going to be bigger, and then smaller again, smaller, smaller, smaller. So where does that electric field inside the wire come from? It actually comes from surface charges on the outside of the wire that get set up because these charges can move around. But this is the important thing about this picture. Delta V loop is 0. Because if I go all the way around this circuit, a complete loop, and I integrate E dot dr around that path, I have to get 0 because the electric field is conservative. And so that's where this delta V loop is 0. This is called the loop rule. Now, if I have a battery, then it's easy to find the change in potential. It's just depends on which way you're going. If I'm going from negative to positive, I have a positive change in potential equal to the EMF of the battery. If I'm going in the direction of current, right, which is the direction, well, actually be the opposite direction of electric field. But if I'm going in the direction of the current, let's just say, because we assume that's the direction of positive charges even though it's not. So if I'm going in the direction of current, I'm integrating in the direction of electric field, so I have a negative change in potential. So delta V battery is, let's just say, EMF, electromotive force is not a force, and then delta V resistor is going to be negative IR if you're in the direction of the current. And that's the loop rule. Now, what about this whole capacitor, not a capacitor thing? Well, the battery fixes this by essentially having a little conveyor belt here, and it takes charge from this side and moves it to that side. And that conveyor belt is a chemical reaction inside the battery, and that's what makes the battery work. And that's what, it's okay to kind of think of it as a capacitor. And I will mention RC circuits at the end. Okay, and then the other rule that we have is, suppose I have these charges that are moving. Let's assume they're positive even though they're not. And then they're over here moving, so we'll call this I1, we'll call that I2. In order to assume that we have a steady state circuit where the current's not changing, then these currents have to be the same. That means that they're going to have to move faster in there, which is why the electric field's greater. So that's our junction rule. I in equals I out. And that's it, right? That's it for the whole chapter. It's more complicated circuits. That one's not that bad. And using these two rules, the loop rule and the junction rule. Now, there is a section in there about RC circuits. Let me just show you why an RC circuit is complicated. And I will make another video where I derive charging and discharging RC circuits and I'll use Python. But it'll be in another video. So it's not really 24 questions, 24 problems. You can skip it if you want to, but since we're talking about it. So imagine that I have a charged capacitor hooked up to a resistor. Well, the loop rule still works, right? So the loop rule says that the voltage across this is Q over C. So, and then I'm going to have, let's say it's charged this way. I'm going to have a current, they use lowercase I, I'm sorry, I, that way. So if I do the loop rule, I get Q over C minus IR equals 0. That's my loop rule. However, that is related to that. Right? The charge in the capacitor, and this is the rate of change of charge. So those two things are related. So I could write this as Q over C minus dQ dt R equals 0. But now I have a complicated differential equation because I have the variable Q that changes with time, and then it depends on the time rate of Q. So you can solve that with differential equations. We can solve that with Python, but that's for the next video. Let's go ahead and do this problem. So I have here 3 branches. So the first thing I want to do, the first thing you should do in a circuit problem is to determine the different currents. So let's just say that I have a current coming out of this battery, and I'm going to call that I1. And then I have one coming out of that battery, I2. And then I have a current that comes through this thing, I'll call that I3. And right there, I have a junction. So that means that the current coming into that junction, I3, is equal to the current coming out. So I1 plus I2 equals I3. I don't know I1, I don't know I2, I don't know I3. Okay? You should have 3 equations, 3 unknowns. Now, there's only one other junction, and it's on the other side of the circuit over here. It's just going to give me the same thing. So it's a redundant equation. I don't need it. Now I can start using loop rules. I'm going to use a loop rule that I know will be useful. I'm going to do a loop rule around this top loop. There's actually 3 different loops, right? I could do a loop around this way. That's 1. I could do a loop around the whole thing. That's 2, or I could do a loop around here, 3. I only need 2 loops to solve the whole problem. I actually need 3 equations, 3 unknowns. Those are my 3 unknowns. I'm just going to do this loop because I know I have a secret here. So let's go from here. Actually, I'm going to go this way. So if I start here and I go across that, I get minus I1R is the potential drop because I'm in the direction of the current. And now I'm going from negative to positive, so I get plus E. And now I'm going to come down here and going against the electric fields to get minus E. And then I'm going against that, and I have plus I2R. And now I'll get back to where I was, and that's 0. So that's an equation that turns out that the E's cancel. And if I move that to the other side, I get I2R equals I1R. Oh, the R's cancel. I1 is equal to I2. Now, maybe you already knew that, right? You're like, hey, obviously they're the same batteries, they're hooked in parallel, they're going to have the same current. But you should be able to show that, right? We shouldn't just say, oh, it is. It is what it is. So I'm going to write that up here, I1 equals I2. That's important. Now, I can go ahead and plug that in up here, and I can say I1 plus I1 is equal to I3. Because if I substitute in I1 for I2, I get that. Or I1 equals I3 over 2. And I2 equals I3 over 2, because it's the same thing. I'm making a lot of progress. I don't have any values, but I made a lot of progress. Now let's do one more loop. I'm going to go this way around the big loop. Okay, so I'm going to start there. I'm going to use the loop rule. I have I'm in the same direction as the current. So I have minus I1. I'll go ahead and write this as minus I1R. Now I'm going to cross that battery, plus E. Now I'm going to go in the same direction as this current, I3. So it's going to be minus I3R, capital R, and that's going to be equal to 0. But I can go ahead and substitute. I can substitute I1 as I3 over 2. I'm going to do that. So I have minus I3 over 2R. That's a subscript. that's R, plus E minus I3 R equals 0. So let's just move those to the other side, and I get E equals I3 times R over 2 plus R. So that's I have my current. I don't know R, right? But I know this value, I know that. So I actually don't know everything, and we're gonna find that. But then I do know that. Okay. So that's kind of solving for the whole thing. If I want, I could write. Well, let's just put that in a box for right now. Let's think about it. So what we want to do is to maximize power. So remember that the power through this resistor, power is I times V, the voltage across that. But the voltage across that is going to be I3R. So it's going to be I3 squared times R, and the resistance right there. Well, let's solve this for I3. I3 is going to be E over R over 2 plus R. So if I put that in up here, I get power is I3 squared, which is going to be E squared R over 2 plus R quantity squared. And this is my power as a function of R, capital R, right? I don't know lowercase r, but I know everything else. So I could just plot this and find out when it's a maximum. But if we have a function and we want to find the max or min, we could use the max-min problem, right? So the max-min problem says if I take the derivative of this with respect to capital R and set it equal to 0, that will be either a maximum or a minimum. And let's just assume it's a maximum. We only get one answer, right? Hopefully it's a maximum. So that's what we're going to do. Let's erase all this. And I'm going to write that up here. Am I on the screen? Yeah. P, and I'm going to put this PR, right? It's a function of R. It's equal to a constant E squared R over 2 plus R squared. Now I'm going to take the derivative, and I don't like the quotient rule because I never remember it. So I'm going to change this. You don't have to change it. I'm going to change it. I'm going to write this as E squared R over 2 plus R to the minus 2. Because then I can think about things better. So if I take the partial of P with respect to R, or you could just say the derivative, it doesn't really matter. Well, I have a product here. I have this term multiplied by that, so I'm going to have to use the product rule. So let's take the derivative of that first term. I get E squared times R over 2 plus R to the negative 2. And now I'm going to take this term times the derivative of that. So this is going to be minus, because I'm going to take the derivative of that, minus 2 E squared R times R over 2 plus R to the negative 3. And now I've taken the derivative of the inside. But the derivative of this with respect to R is just 1, because I only have 1 in there. So that's that. So now I want to set this equal to 0. So let's set that equal to 0. And if we do that, I can write this as, I'm going to put these back the way they were. So I'm going to move them back down as fractions. E squared over R over 2 plus R quantity squared is 2 E squared R over 2 plus R cubed. Now I can multiply both sides by R over 2 plus R squared, and I get E squared equals 2E R over 2 plus R, right? Because that's going to cancel, and then I have a squared over cubed, so that just leaves me with that. And I want to solve this for R, so now I'm going to multiply both sides by the bottom, and I get E squared R over 2 plus E squared. Oh, that's squared. E squared. Wait. Oh, yeah. R. I lost where it was. And then I have just this. 2 E squared R. So the e squareds cancel. Nice. I'm going to subtract that from both sides, and I get r equals r over 2. Because I had a 2r, and then I subtract r. So I get r is r over 2. And now let's just go ahead and put in our values, because I know r is 0.3, and I know 2 is 2. So I get 0.15 ohms. And then the other thing said, well, what is that maximum power? Now I can just go back to my power equation up here. I can say power of 0.15, and I'm going to put in all my values. 12 squared, 0.15 over 0.15, right, because that's 0.3 plus 0.15, so I get 0.3 quantity squared. And let's put that in the calculator. Okay, drop, oops, enter, drop. So I get 12 squared, 0.15 times 0.3 squared. Is that squared? Yeah. Divided by. I get 21.6 watts. It was kind of fun. The circuit wasn't too bad, but I liked it because it had the Maxmin stuff in there. The end. Like I said, there will be a RC circuit derivation using Python and differential equation. I'm going to do it both ways, just for you.